Hi all. Uh, uh, in this video, we're going to see a paper called QLoRA Efficient Fine Tuning of Quantized LLMs. This is one of the best paper in NIPS 2023. So let's see what this paper says about. So we all know that large language models have a huge parameters, like almost like 175 billion parameters for ChatGPT 3. For example, large language models of 65 billion parameters might require 780 GB of GPU memory during training. So, which is computationally and memory oriented, prohibitively expensive during the fine tuning. So the just give some overall view. So these large language models are pre-trained generally and kept those parameters frozen, and during that for different applications those parameters are fine-tuned for a very less number of efforts. But if we involve a full number of parameters, it is going to be prohibitively expensive in terms of memory and computational time. So for this, they adapted two techniques. One is quantization methods, where they represent those memory weights into a low bit representations instead of 16-bit representation. They are going to go for a 4-bit representations without sacrificing the performance. The second technique is, as usual, we saw in the last video, low rank adaptations. So this is the paper that we saw in the last video, like how these low rank adaptations during fine tuning, because it's not necessary to update all the full weights during fine tuning. Only a certain number of weights can be updated. Because of this hypothesis that many of the parameter updates are lies in the low dimensional space, and mathematically this is represented in this way, because this weight is a pre-trained weight, and the update is happening upon this additional perturbations. That perturbation matrix can be represented as a matrix decomposition, and these matrices are rank 1 update matrices, for example. So that during the matrix data multiplication from the input, so this can only base this will be frozen, and this update will be happening. So this is the technique similarly utilized here. But in addition, that additional that memory weights are not represented in the memory in the full 16-bit things, and instead of that they are going to represented in a context 4-bit in such a way that the performance is not degraded. So these are the so by this what they claimed is, for a 16 billion parameters during fine tuning, instead of occupying 780 GB GP of memory, only 48 GB would be sufficient enough without degrading during the runtime performance. So these are the three contribution. In addition to that, um, I introduced in the last paper, like low dimensional adaptations. So this is a 4-bit normal new way of quantizing that weights, instead of going for 4-bit integers or 4-bit floats. Then another concept is called double quantizing, quantizing the previous quantized constant, so that the first quantized could have a zero point 0.5 bits per parameter, and this would be double quantization would ended up in 0.37, which has an additional saving of 3 GB for a 65 GB billion model. So, and additionally, how the memory transfer between CPU and GPU also optimized. So these combined effects with that low rank adaptations gives memory efficient fine tuning in a large language model. So this is a full fine tuning where all the 16 bits and also all the parameters are updated. Here, still the bits are not quantized, uh, but that low rank adaptation only a few parameters are updated. But here, all these methods are combined here, where memory efficient between CPU and GPU take place, and low rank adaptations only a certain weights are updated, and updated on only on weights which are already quantized and represented in a 4-bit transformers. So hopefully we'll see in some other videos of the best NIPS paper of 2023. Thank you.